Welcome to our lecture series on Earth's dynamic surface. Today, we are diving into geomorphic movements. If you look outside, the landscape might seem permanent and unmoving, but Earth's crust is actually constantly evolving. This change is driven by two main types of forces. First, we have endogenic forces, which emanate from deep below the Earth's surface. Second, we have exogenic forces, which operate above the surface. Together, these forces cause physical and chemical changes to our planet's structure. Some of these changes are imperceptibly slow, like the folding of rock. Others are gradual, like a river eroding a canyon. And some are incredibly sudden and violent, like earthquakes and volcanic eruptions.
Before we get too deep into the mechanics, let's establish some key terminology. The word geomorphic simply relates to the form of the landscape and natural features of the Earth. When we talk about geomorphic agents, we mean mobile mediums. Think of running water, moving glaciers, or strong winds that actively remove, transport, and deposit materials. Geomorphic processes are the actual physical and chemical actions taking place, like weathering or faulting. Finally, geomorphic movements refer to the large-scale changes that result from all these processes working together over time. Let's focus our attention underground. Endogenic geomorphic movements are the large-scale shifts on the Earth's crust brought about by forces deep within the planet. The word itself tells you exactly what it is. Endo means internal, and genic means origin, so these are Earth-shaping movements of internal origin. The specific processes driven by these deep internal forces, such as the folding and faulting of massive rock layers, are what we call endogenic geomorphic processes. You might be wondering, what exactly is powering these massive internal movements? The ultimate engine is the Earth's internal heat. About half of this intense heat is generated by radioactive decay happening deep within the planet's core and mantle. Additionally, the immense force of gravitation creates severe pressure gradients. As you move through the various layers of the Earth, you encounter significant differences in both temperature, known as geothermal gradients, and pressure. These variations naturally give rise to differences in density within the molten rock. Those density differences we just mentioned are crucial because they create convectional currents within the Earth's mantle. Imagine a pot of boiling water, where hot fluid rises, cools, and then sinks back down. A similar process happens with molten rock. These massive convection currents act like a conveyor belt, driving the movement of the lithospheric plates above them, a process we know as plate tectonics. Furthermore, as the Earth rotates, the Coriolis effect influences exactly where these convection currents travel. Ultimately, the destination of these currents determines exactly where on the surface we will see endogenic movements occur. To keep all of this organized, geologists classify Earth movements using a specific hierarchy. Earth movements broadly split into endogenetic, from within, and exogenetic, from the outside. Looking just at the endogenetic side, we divide these into two categories based on time: diastrophism, which are slow, gradual movements, and sudden movements, which happen violently and quickly. Diastrophism is further broken down into epirogenec, or continent-forming movements, and orogenic, or mountain-building movements. Meanwhile, sudden movements include the dramatic events we are all familiar with: earthquakes and volcanoes. Let's look closer at diastrophism. This term refers to the slow, relentless deformation of the Earth's crust. It encompasses processes like folding, faulting, fracturing, and warping, which is the bending or twisting of a massive area of land. Unlike a sudden earthquake, diastrophic movements are incredibly gradual, often stretching out over thousands or even millions of years. Because it happens so slowly, we usually only realize it occurred by looking at the geological record. The most obvious evidence of diastrophism is found in sedimentary rocks. When we see these horizontal layers bent, broken, or tilted at steep angles, we know diastrophic forces have been at work. All processes that move, elevate, or build up portions of the Earth's crust fall under diastrophism. We can categorize these into four main processes. First are orogenic processes, which involve mountain building through severe folding of the crust, usually affecting long, narrow belts of land. Second are epirogenec processes, which involve the uplift or warping of massive parts of the crust in a simpler deformation. Third, we include the local, relatively minor crustal movements associated with earthquakes and volcanism. And fourth, plate tectonics, which involves the vast horizontal movements of the crustal plates themselves. Now, let's unpack epirogenic movements, commonly known as continent-forming movements. Unlike forces that push sideways, epirogenic movements are radial, meaning they act along the radius of the Earth, moving straight up or straight down. If the movement is towards the Earth's center, we get subsidence, or sinking land. If it's away from the center, we get uplift. This vertical motion causes massive upheavals or depressions, creating broad, wavy undulations across the landscape, with very little actual folding of the rock. Because this primarily affects the broad, stable central parts of continents, known as cratons, we call it continent forming.
How do we know uplift actually happens? The evidence is written right into the landscape. Geologists look for raised beaches, elevated wave-cut terraces, sea caves, and beds of marine fossils that are now sitting high above the current sea level. In India, excellent examples of raised beaches can be found along the Kathiawar, Nellore, and Thirunel Valley coasts. We also have historical evidence. Several places that were bustling coastal seaports just a few centuries ago are now located miles inland because the land beneath them rose. For instance, Karinga, Kaviaripatnam, and Korkai were all flourishing port cities 1,000 to 2,000 years ago, but are now completely landlocked. Conversely, we also have stark evidence of subsidence, where the land sinks downward. We can find submerged forests, drowned river valleys, and even human buildings resting underwater. A famous historical example occurred in 1819, when a massive earthquake caused a large part of the Rann of Kutch to suddenly submerge. We also find stratigraphic evidence, like beds of peat and lignite, which are formed from land-based plant matter, buried deep below the current sea level in places like Tirunelveli and the Cinderbans.
The evidence for subsidence continues across the globe. Look at the Andaman and Nicobar Islands. They were once connected to the Arakan coast, but became isolated islands when the intervening land sank beneath the ocean. On the east side of Bombay Island, researchers have found actual trees embedded in the mud 4 meters below the low water mark, with similar submerged forests found on the Tirunelveli coast. Large, shallow bodies of water, like the Gulf of Mannar and Palk Strait, were actually dry land that submerged in geologically recent times. We even see this affecting human history, as parts of the ancient town of Mahabalipuram near Chennai now sit quietly beneath the waves.
Shifting gears from the vertical epirogenic movements, we have orogenic movements, which are mountain-forming movements. These are much more complicated deformations of the Earth's crust. They are primarily associated with crustal thickening, which happens when tectonic plates converge and crash into one another. Unlike radial movements, orogenic movements act tangentially or sideways along the Earth's surface. When these tangential forces pull away from each other, it creates tension, which tears the rock and produces fissures. When the forces push towards each other, it creates compression, which crumples the rock and produces massive folds, eventually lifting up mountain ranges.
While diastrophism takes thousands of years, sudden movements happen in the blink of an eye, geologically speaking. These violent events occur almost exclusively at the margins of lithospheric plates. Because they release massive amounts of energy, they cause considerable deformation over a very short period. These plate boundaries are highly unstable zones. The root cause of this instability is the immense pressure created deep below, as the convectional currents in the mantle constantly push and pull the magma against the crust above.
The most common sudden movement is an earthquake. As plates push against each other, stress accumulates in the rocks. When that surplus stress finally overcomes the strength of the rock, it snaps, relieving the pressure through weak zones in the crust. This releases a massive burst of kinetic energy that travels to the surface as seismic waves. The physical results can be drastic. Earthquakes can cause instant uplift or subsidence, alter the contours of the land, change the course of rivers, and trigger landslides. For example, an 1885 earthquake in New Zealand caused an instant land uplift of up to 3 meters, while an 1891 earthquake in Japan caused the ground to suddenly subside by 6 meters.
The other major sudden movement is volcanism. A volcano forms when pressurized molten rock, or magma, from the Earth's interior finds a way to escape through narrow vents and fissures in the crust. When it breaches the surface, it isn't just lava that comes out. These eruptions are highly complex, releasing massive amounts of steam and toxic gases like hydrogen sulfide, sulfur dioxide, and carbon dioxide. They also violently eject pyroclastic material, which includes dense clouds of hot ash and glowing lava fragments blasted high into the air. Understanding these powerful internal forces sets the perfect stage for us to explore what happens when forces from above the surface start tearing these landscapes down.
Moving right along to the forces that shape the crust from the outside, we encounter exogenic geomorphic movements. Unlike internal tectonic forces, these processes are driven by forces above the surface, primarily wind and water. The ultimate engine for all of this is the sun, whose energy dictates the weather patterns that induce stress in Earth materials. While the daily effects of wind and rain might seem small and slow, over the long run, they cause severe fatigue in rocks, leading to massive changes through weathering and erosion. All of these exogenic processes fall under a broad umbrella term called denudation. The word denude simply means to strip off or uncover. How quickly or severely a landscape is denuded depends heavily on the properties of the rocks themselves. Physical properties, like the presence of faults, joints, or how permeable the rock is, play a huge role. Similarly, the chemical makeup of the rock dictates how susceptible its minerals are to corrosion.
We can break denudational processes down into three main categories, each driven by specific forces. Weathering is driven by a combination of gravitational forces, molecular stresses, and chemical actions. Mass movements, like landslides, are almost entirely driven by the sheer force of gravity pulling material down a slope. Finally, erosion and transportation are driven by kinetic energy, the actual movement of wind, water, or ice carrying material away. Let us focus specifically on weathering. Weathering is the disintegration of rocks, soil, and minerals. The most important characteristic to remember here is that weathering is an in situ, or on-site process. This means the rock breaks down right where it sits, with little to no actual movement of the material. Once the material is carried away, that becomes erosion. Weathering itself is categorized into three major groups: physical, chemical, and biological, which often work hand in hand.
Why does weathering matter? First and foremost, it is the crucial first step in creating soil from solid rock. Without it, terrestrial life as we know it would struggle to exist. It also weakens rocks, which makes it much easier for humans to mine and exploit natural resources. Furthermore, weathering naturally enriches the soil and can even concentrate valuable minimal ores by leaching away the unwanted, less valuable minerals over time. Diving into physical weathering, this involves the purely mechanical breakdown of rocks. The chemical composition of the rock does not change, it is simply broken into smaller pieces. This happens because of various stresses. Temperature changes cause molecular expansion and contraction, while pushing and pulling forces create shear stress. Other major drivers include the expansion of freezing water, the growth of salt crystals, and even the physical activities of plants and animals. One fascinating type of physical weathering is exfoliation due to pressure release, also known as unloading. Imagine intrusive igneous rocks that formed deep beneath the Earth's surface under tremendous pressure. As the overlying rock is eroded away over millions of years, that immense weight is lifted. This vertical pressure release allows the newly exposed upper layers of the rock to expand outward. As they expand, they fracture parallel to the surface, causing large sheets of rock to peel away in a process called sheeting. Exfoliation can also be caused by thermal stress. This is driven by extreme temperature variations between day and night or between seasons. As the rock heats up under the sun, it expands. As it cools at night, it contracts. Because rocks are poor conductors of heat, only the outer surface expands and contracts significantly, while the deeper rock remains stable. This differential movement causes the outer layers to peel off. You will see this most often in dry climates and high elevations, where temperature swings are drastic. What happens when a rock is made of a patchwork of different minerals? We get granular disintegration. Dark-colored minerals absorb heat much faster than light-colored ones, so in a single piece of rock, the dark grains are expanding more than the light grains right next to them. This creates intense microscopic stress, eventually causing the rock to crumble and separate grain by grain. Moving to colder environments, we encounter frost weathering. This is a collective term for any weathering process driven by the presence of ice. The mechanism is simple but incredibly powerful. Water seeps into the tiny pores and fractures of a rock. When the temperature drops below freezing, that water turns to ice and expands in volume. This expansion acts like a hydraulic jack, exerting tremendous outward pressure on the rock walls. This expansion leads to frost wedging, where existing cracks are literally wedged further apart with every freeze-thaw cycle. Over time, these repeated cycles severely weaken the structural integrity of the rock. Eventually, the rock will break apart along its natural joints and fractures. When the rock splits into large angular pieces, we call this block separation, or block disintegration. In areas with particularly severe frost, the rock doesn't just break into large blocks, it undergoes shattering.
The rock disintegrates rapidly along weak zones, producing highly angular pieces with very sharp corners and edges. Gravity pulls these shattered fragments down steep slopes, where they pile up at the foot of mountains. These massive, loose piles of jagged rock fragments are known as scree.
A process very similar to frost wedging happens in hot, dry deserts, known as salt weathering. Here, saline water seeps into rock cracks. When the intense desert heat evaporates the water, salt crystals are left behind. As these crystals grow and as they expand when heated, they exert pressure inside the rock pores. This forces the individual grains apart, causing the rock surface to crumble. It is a dominant weathering force in arid climates.
Now, let us transition from physical breakdown to chemical weathering. This involves the actual chemical decomposition of the rock, altering its mineral structure and loosening the bonds between grains. The major processes include dissolution, carbonation, hydration, and oxidation. These chemical reactions do not happen in isolation. They are significantly accelerated by the presence of water, heat, and acids produced by plants, microbes, and the atmosphere. The simplest form of chemical weathering is natural dissolution. In chemistry terms, this is just a solute dissolving in a solvent. When rain falls, minerals that have a high natural solubility, like nitrates, sulfates, and potassium, simply dissolve into the water. They are completely leached out of the rock without leaving any solid residue behind, and the mineral-laden water often flows away to accumulate in drier regions. Solution weathering takes dissolution a step further. While pure water can dissolve some things, solution weathering specifically occurs when the acting solvent is an acidic solution. An acidic solution has a higher concentration of hydrogen ions than pure water, which makes it far more aggressive and capable of breaking down minerals that would otherwise resist simple water dissolution.
The most common type of natural solution weathering is carbonation. As rain falls through the atmosphere, it absorbs carbon dioxide, creating a weak carbonic acid. When this slightly acidic rain hits limestone, which is calcium carbonate, a chemical reaction occurs. It converts the limestone into calcium bicarbonate, which dissolves in the water and is carried away. Underground, this process carves out massive empty pockets, forming cave systems and karst topography. Interestingly, this process is highly active in glacial environments because colder water can hold more dissolved carbon dioxide.
Human activity has drastically accelerated solution weathering through anthropogenic means, primarily acid rain. Natural rainfall is already slightly acidic, with a pH of about 5.6. However, when industrial emissions like sulfur dioxide and nitrogen oxides mix with atmospheric moisture, they create much stronger acids, dropping the rain's pH below 4. This highly acidic rain attacks and dissolves stone structures and natural rocks at an unnaturally rapid pace.
Next is hydration, which is the chemical addition of water directly into the molecular structure of a mineral. When the hydrogen and hydroxide ions attach to the mineral physically expands. For example, iron oxides convert into iron hydroxides, which take up more space. Because this process is reversible, wet and dry cycles cause the mineral to repeatedly swell and shrink. This internal stress causes rock fatigue and heavily assists physical weathering processes like exfoliation.
Hydrolysis is a bit different. Here, a water molecule is actually consumed in the reaction to split a larger mineral molecule apart. When pure water reacts with silicate or carbonate minerals, it breaks them down, dissolving the original mineral structure. On a planetary scale, biological hydrolysis is incredibly important because it regulates the amount of carbon dioxide in the atmosphere, playing a major role in controlling the Earth's climate over long geological periods.
Then we have oxidation and reduction, which dictate the colors of many landscapes. Oxidation occurs when a mineral combines with oxygen, usually in the presence of water. The most familiar example is iron rusting, which is exactly what gives red soils their distinct color. Conversely, if these minerals are buried in an environment completely lacking oxygen, like deep below the water table or in stagnant swamps, reduction occurs. Under these conditions, that rusty red iron changes to a greenish or bluish-gray color.
Finally, we cannot ignore the biosphere's role. Biological weathering involves both mechanical and chemical breakdown by living organisms. Mechanically, tree roots wedge into crevices to pry rocks apart, while burrowing animals like rodents and earthworms constantly churn the soil, exposing new rock surfaces to the elements. Chemically, lichens and mosses secrete acids to extract nutrients from bare rock, and decaying organic matter produces humic acids that further dissolve minerals. This biological activity perfectly sets the stage for the next phase of geomorphic movement.
Let's look at the concept of mass wasting, also known as slope failure or mass movements. This is the process where unconsolidated materials like soil, sand, rocks, and regolith, which is the layer of loose solid material covering bedrock, move down a slope. The primary driving force here is gravity. Depending on how the material moves, mass wasting can be categorized into creeps, flows, slides, and falls.
For mass wasting to occur, the forces at play must tip out of balance. Materials on a slope have their own natural resistance to disturbing forces, known as shearing resistance. They will only yield and move when the downward pull of gravity becomes greater than this resistance. The timescales for these movements vary drastically. A debris flow or mud flow can happen in just a few terrifying seconds, while mass wasting along stable mountain slopes might take hundreds of years, eventually leaving behind large, fan-like alluvial structures.
Several natural conditions make a slope more prone to mass movements. Slopes composed of weak, unconsolidated materials or thinly bedded rocks are naturally fragile. The presence of geological faults, steeply dipping beds, or vertical cliffs also increases the risk. Add in environmental factors like abundant precipitation, torrential rains, and a scarcity of vegetation to anchor the soil, and you have a prime environment for slope failure.
Beyond the underlying conditions, there are specific activating causes that trigger these movements. One major trigger is the removal of support from the base of a slope, which can happen naturally through erosion or artificially through excavation. Increasing the steepness or height of a slope also destabilizes it. Additionally, overloading the top of the slope with extra weight, whether from natural deposits or artificial filling, such as the construction of hydroelectric projects in the Himalayas, can push the slope past its breaking point. Water plays a massive role in triggering mass wasting. Heavy rainfall leads to the saturation and lubrication of slope materials, drastically reducing their friction. This is a common cause of landslides in the Western Ghats during the monsoon season. Excessive natural seepage can have a similar effect. On the other hand, sudden shocks from earthquakes, which are frequent in the tectonically active Himalayas, or artificial vibrations from explosions and mining machinery can instantly shatter a slope's stability. Human interactions with water bodies and vegetation also trigger mass movements. A heavy, rapid drawdown of water from lakes, reservoirs, or rivers can cause the slow outflow of groundwater from under the adjacent slopes, leading to collapse. Furthermore, the indiscriminate removal of natural vegetation is a major culprit. For example, in the Western Ghats, replacing natural forests with plantation agriculture drastically reduces slope stability because plantation crops have shallow roots and lower tree density, offering far less structural support to the soil. Now let's categorize these movements by speed, starting with slow movements like creep. Creep typically occurs on moderately steep, soil-covered slopes. The movement of soil or rock debris is extremely slow, so slow that it's imperceptible to the naked eye as it happens. We usually only notice creep through extended observation of its effects, such as fence posts, trees, and telephone poles slowly leaning downslope from their original vertical positions. Depending on the material involved, we can identify several specific types of creep, such as soil creep, talus creep, and rock glacier creep. Another important slow movement is soliflection. This involves the slow, downslope flowing of soil mass or fine-grained rock debris that is heavily saturated and lubricated with water. Soliflection is especially common in moist, temperate areas where the surface of deeply frozen ground melts or where long-continued rains saturate the upper soil layers. Moving on to rapid movements, these are most prevalent in humid climatic regions and can occur over gentle to steep slopes. One type is an earth flow, which is the movement of water-saturated clay or silty materials down a hillside. As the material slumps, it often creates step-like terraces, leaving behind curved, arcuate scarps at the top and forming a bulging accumulation of material at the toe of the flow. On steeper slopes, even soft bedrock like shale or deeply weathered igneous rock might slide. When heavy rainfall hits an area with thick layers of weathered material and little to no vegetation cover, mud flows can occur. These materials become completely saturated and flow down along definite channels, looking very much like a river of wet cement within a valley. Mud flows can move slowly or very rapidly. When they burst out of mountain channels onto the flatter piedmont or plains, they spread out and can be incredibly destructive, easily engulfing roads, bridges, and entire houses. A specific and terrifying type of mudflow is a lahar, which occurs on the slopes of erupting or recently erupted volcanoes.
When heavy rains mix with loose volcanic ash, dust, and rock fragments, they turn into a dense slurry. These streams of mud flow rapidly down the volcano's flanks, causing massive destruction to human habitations below. Devastating lahars have been observed in recent decades, following eruptions in the Andes Mountains of South America and the Rockies in North America. Another rapid movement is the debris avalanche. This is characteristic of humid regions, and it can happen whether the slope is covered in vegetation or not. Debris avalanches occur in narrow tracks on very steep slopes. You can think of them as being very similar to a snow avalanche, but made of earth and rock. Because of the steepness and the mechanics of the fall, a debris avalanche can move much faster than a typical mudflow, leaving little time for evacuation.
Landslides are rapid, highly perceptible movements, but unlike mudflows, the materials involved are relatively dry. The size and shape of a landslide depend on rock discontinuities, weathering, and slope steepness. We categorize landslides by how the material moves. The first type is a slump. In a slump, one or several units of rock and debris slip downwards, but they undergo a backward rotation relative to the slope. Imagine sitting in a recliner chair tipping backward as it slides down a hill. Other types of landslides include debris slides, where earth debris rapidly rolls or slides downward without that backward rotation we see in slumps. Then there is a debris fall, which is exactly what it sounds like, a nearly free fall of earth debris from a vertical or overhanging cliff face. Finally, we have rock slides, which involve individual rock masses sliding down specific bedding planes, joints, or fault surfaces. On oversteepened slopes, rock slides are incredibly fast and highly destructive.
It is important to clarify the relationship between weathering and mass movements. Gravity exerts its downward force on all matter, whether it is solid, pristine bedrock or the broken-down products of weathering. Therefore, weathering is not a strict prerequisite for a mass movement to occur. However, weathering severely weakens the rock, meaning mass movements are far more active and frequent over weathered slopes compared to unweathered solid materials. You might be wondering, is mass wasting just a type of erosion? The answer is no. There is a distinct difference. Erosion involves the transportation of material by a mobile geomorphic agent, like running water, moving glaciers, wind, waves, or ocean currents. Mass movements, on the other hand, are aided solely by gravity. No geomorphic agent participates in the actual process of a mass movement. Therefore, even though material shifts from one place to another, mass movements do not fall under the category of erosion.
Looking at India specifically, debris avalanches and landslides are incredibly frequent in the Himalayas. There are several geological reasons for this. First, the Himalayas are a young, tectonically active mountain range, meaning earthquakes frequently destabilize the slopes. Second, they are mostly composed of sedimentary rocks and unconsolidated or semi-consolidated deposits, which are inherently weak. Combined with extremely steep slopes, the region is highly susceptible to massive slope failures.
In contrast, the Nilgiris and the Western Ghats along India's west coast are relatively tectonically stable and made of very hard rocks. Yet they still experience landslides and debris avalanches, though less frequently than the Himalayas. Why? Many slopes here feature almost vertical cliffs and escarpments. They experience pronounced mechanical weathering due to wide temperature fluctuations. Furthermore, they receive incredibly heavy rainfall over short periods during the monsoon, leading to direct rock falls and saturated debris slides.
When analyzing landslides in these regions, a topic frequently tested in exams like the UPSC mains, we cannot ignore human or anthropogenic activities. Natural factors set the stage, but human actions often pull the trigger. Activities such as aggressive road construction cutting into the base of slopes, expanding tourism infrastructure, and replacing deep-rooted natural forests with shallow-rooted plantation agriculture drastically reduce slope stability and accelerate the rate of mass wasting across both the Himalayas and the Western Ghats.
To wrap up our discussion on mass wasting, remember that these movements are driven fundamentally by gravity, distinguishing them from erosion, which requires a transport agent like water or wind. We've seen that mass wasting spans a huge spectrum, from the slow, imperceptible creep of soil to terrifyingly rapid mudflows and rock slides. The stability of any slope is a delicate balance of material strength, slope angle, and water saturation, a balance that is increasingly being disrupted by human activities and infrastructure development.